The objective today is to connect the properties of computationally hard problems with desirable properties for encryption. So think back to what you know about the math behind public key cryptography. How close is this to the real thing? Our scheme here most closely resembles the RSA public key encryption system. Now, RSA doesn't stand for anything related to cryptography. It's just the initials of the last names of the three people who invented it, Rivas, Shamir, and Adelman. So the first thing, or the second thing technically, I want to point out is that RSA does rely on multiplication and modulo, but instead of just multiplying numbers plainly, the private keys and the secret numbers are used as exponents when multiplying large numbers, which makes even bigger numbers that are even harder to reverse after modulo. Your think right share here is, in an RSA algorithm, what numbers are used as exponents? And as a quick refresher here, I put down some prime numbers. And if you remember from the last video, I said I like to root for athletes who have prime numbers for their jersey numbers, like Paul George with 13 or Chris Paul with number 3. So the third thing to point out to you guys is that rather than finding the multiplicative inverse to crack RSA, you need to find the prime factors of a very large number. That is, given a large number, find two prime numbers that when multiplied together yield that same number. This is a much harder problem computationally than finding the multiplicative inverse, which is what our widget does. Your think right share here is, how comfortable are you with this need for prime numbers? And the last thing to point out is that the actual numbers used are over 75 digits long. That's 256 bits. So if you think you can fathom how big a number with 75 digits is, you can't. The distance to the edge of our solar system in inches is only a 14-digit number. My think right share for you is, how many decimal digits would you need to represent a binary number? That is 256 binary digits long. So by and large, whenever you get overwhelmed with the math of it all, just think some sort of math magic is happening to make public key cryptography work. You will not be tested on your ability to plug and chug using that formula of the RSA algorithm. But it's good for you to know that that is the process in which we use, so a stranger in one part of the world can communicate with a stranger in another part of the world, and nobody in between can understand what they are talking about. So now let's turn our attention to a classic problem in computer science, the traveling salesperson problem. See, I dressed up for it today. You'll solve small instances of the problem, try to formulate algorithms to solve it, and discuss why these algorithms take a long time for computers, and humans, to compute. You'll see how the TSP grows in size much faster than the problem of adding characters to a password. As a think right share here, and as a check for understanding, what is an algorithm again? In this final algorithm, Detour, we'll study a problem for which there is no known algorithm to solve it, other than brute force. The number of possible solutions grows extremely fast even for small inputs, and quickly becomes unreasonable to solve, making it a computationally hard problem. The ideas of computationally hard problems are leveraged for encryption to make ciphers that take an unreasonable amount of time to crack, as in thousands of trillions of years. But computationally hard problems are also important in their own right. There are many problems for which we wish we had a reasonable algorithmic solution, especially in medical fields, and we're still on the hunt to find them. No one has yet mathematically proven whether or not the problems we currently think are hard actually are. So your think right share here is, on a scale of 1 to 10, 10 being you're great, how do you feel you are at math? So let's start with just an image. Think right share, predict what you think the traveling salesman problem could be about. We learn that the longer a password is, the harder it is to crack. This is because every character you add multiplies the number of possible passwords, the number of possibilities for that character. That's pretty fast growing. Computationally hard problems are problems that force a computer to run through many possibilities to find the right answer. In cryptography, our desire is to have an encryption function that is easy to compute if you have the key, but really hard if you don't. So here's the history of the traveling salesman problem. This problem was first formulated in 1930 and is one of the most intensely studied problems in optimization because it has many applications in the real world. Almost any business that involves transportation of any kind is concerned with this problem because there are direct costs, that is in time, money, and resources, to taking inefficient paths to visit all the nodes you need to get to. And in our context today, think of nodes as the houses the salesman is supposed to visit. So, for example, a mail carrier delivering mail must go to each house exactly once, needs to end up at the starting location, and wants to minimize the length of the route. When you are running errands to different stores or picking up friends to bring them to your place for a party, you need to visit each location once, return to where you started, and you must want to optimize your route. Your think right share here is, can you think of a similar problem or example from real life? And if you're really struggling with thinking of another example of where the traveling salesman is important, just think of the companies of FedEx and UPS. Okay, so this problem imagines that a salesperson starting at his or her home or office needs to visit a number of customers at different locations. The goal is for the salesperson to visit each location exactly once and end up back where they started as efficiently as possible without retracing any part of the route. The problem is, given a graph of nodes and edges where the weights of the edges represent some cost, that is in distance, time, or money, find the set of edges that make the lowest cost tour of all of the nodes. A tour is a route that visits each node exactly once and returns to the starting node. So this graph shows the direct routes between stores and the distance of each route. You can assume any node is your home, so the starting point is wherever you decide here. Here are some possible routes with their total distances that visit every node once and return to wherever you start. So notice the difference between 31 and 24. So the shortest route that visits every node once and returns to wherever you started is this one, where the numbers end up as 21. So now I'm asking you to give me another unique route that is not 21, 24, or 31, and write that up in Canvas. If I asked you how you arrived at your solution, you might say, I tried a bunch of different paths and kept track of the shortest. Or some form of a greedy algorithm. I want to avoid the large edge, or I want to use that small edge. These are good strategies, but they can always be thwarted with the question, how do you know for sure it's the shortest route? So what makes this problem harder than the shortest path problem? First of all, you need to make a closed path route of all vertices without revisiting vertices. This is a harder thing to do than just finding a path from one to another. And then second, you don't know where to start. Any edge could be part of the shortest tour, and once you pick an edge to start with, you still have no way to choose the next one. There is no way to eliminate possibilities from the start or as you go. The only algorithm that is known to find the absolute shortest tour every time is brute force, generating every possible tour and comparing them. Many people for many years have tried to design an algorithm that works in all cases to find the exact optimum route for the traveling sales problem with no success. So in your own words, what does brute force mean? Okay, so let's consider a version of the problem faced by, say, an airline. For an airline, there are cities all over the world, and you can fly from one directly to another. So for an airline, there is a possible path that connects every possible node. We say the graph is fully connected. The picture above shows the difference between 4 nodes and 5 nodes. With just 10 nodes, this grows to about 181,000 possible tours. With 26 nodes, this grows to a 25-digit number, and in red right here is a 25-digit number. So your think right share, using just the picture up here, what is the difference between these two models, this one and this one with 5 nodes? Now, computers work fast, but they have limits. In computer science, we have an actual mathematical hard line between reasonable and unreasonable runtimes. So let's start with the reasonable. Reasonable means the number of things a computer has to do is proportional to the size of the input to the problem. For example, the minimum spanning tree and the shortest path problems are reasonable because they had algorithms that solved them by considering every edge in the graph once. The amount of time it takes is proportional to the number of edges. If the number of edges is n, even if there was an algorithm that had to look at the edge n to the second times or n to the third times, that's still reasonable. Your think, write, share here is I want you to think of some limiting factors to a computer's ability to solve mathematical problems. And I want to encourage you to be as creative as possible with this one. If you need a little hint, think about what I always say in class about cryptocurrency, that a lot of people who mine, that is the ones using the proof of work type of cryptocurrencies, these people mining will spend much more in electricity than they earn back in the coins they find. Okay, so let's talk about unreasonable now. This means the number of things a computer has to do grows as an exponent of the size of the input. So if you discovered that an algorithm made the computer do 2 to the n things, that's not reasonable because it means every time the size of the input, n, gets bigger, the solution gets massively further out of reach. N factorial is another running time that is considered unreasonable. In real life, unreasonable problems would take a modern computer trillions and trillions of years to churn through all the possibilities. Your think, right, share is what's the difference between reasonable and unreasonable. So that was it for today. It's good to know that there are still problems out there for people of your generation to solve, like this traveling salesman problem. Who knows, one of you out there may be the one to solve it, and you'll go down in the history books as one of the greatest minds ever, I think. So, with that said, think about which one of the IB profile attributes reflect the lesson of the day. And when you're done with that, here's your DOL. First, describe what it means for a problem to be computationally hard, and then give me some strategies people use to solve these large problems. And for your last one, why are computationally hard problems important in encryption strategies?